Welcome back to The Explainer. Today we're going to unravel a really fascinating scientific mystery. I want you to imagine a single mathematical term, literally just one letter that completely changes its entire identity depending on exactly whose clipboard it happens to be written on. We are talking about the elusive z-value. As focused learners, you know how crucial precision is. And today, we're going to look at how that precision completely shifts its shape the moment we cross the boundaries of different scientific disciplines. Okay, let's dive into this. What exactly is a z-value? Well, if you were to walk into a university right now and ask two different scientists this exact question, you might actually get two completely different yet equally correct answers. Crazy, right? That's because this term moonlights in two completely separate fields of study. It's a fantastic reminder that in science, context isn't just helpful, it is absolutely everything. You can think of this as a tale of two Z's. As we look at the source data, we're effectively standing at a pretty fascinating fork in the road of scientific methodology. Down one path, we've got the realm of pure data analysis and abstract mathematics. But down the other path, we enter the highly physical, super high-stakes world of food science and pharmacology. To put it in perspective, in the realm of statistics, the z-value is entirely about a data point's distance from the mean. It's a spatial thing. But cross over into microbiology and food science, and suddenly, bam, the z-value measures thermal resistance for microbes. These are two completely separate ways that professionals approach, measure, and utilize data to solve entirely different problems. Path A, statistical z-scores. To really grasp the whole scope of this term, we first need to take a quick walk down this path to set our baseline. In statistics, a z-value just describes a specific data point's relationship to the mean or the average of a broader group. Specifically, it's measuring how many standard deviations a raw score is below or above that population mean. The formula is actually quite elegant. It just compares a raw score to the population's average and its standard deviation. And the results? Very intuitive. A positive value simply means the data point is above the mean. A negative value means it's below. And a z-value of exactly 0? Well, that tells the statistician your data point is exactly equal to the mean, right on the money. Now for path B, microbial thermal resistance. Leaving pure math behind to travel down this path, the tone shifts dramatically. We're moving from abstract numbers on a page to the very literal, physical reality of destroying dangerous microbes using heat. This right here is the critical science behind food processing and pharmaceutical manufacturing. So the crucial point is how this translates in the lab. In these fields, the microbial z-value is defined as the temperature increase, whether you're measuring in Celsius or Fahrenheit, doesn't matter, that is required to reduce a microbe's decimal reduction time by 90%. We call that the d-value. Simply put, the d-value is the exact time it takes at a certain temperature to kill off 90% of the bacteria. So let's strip away all that jargon for a second. The z-value is basically a precise measurement of a specific organism's resistance to heat. Let's ground this in practical reality. Take the number 10. The z-value tells us how susceptible a specific spore population is to temperature changes. For instance, if we know the z-value of a spore population is 10 degrees, then increasing our sterilization temperature by exactly 10 degrees will result in a log reduction of the d-value. That means the d-value drops by one full factor of 10. That is a massive 90% drop in survival rate, achieved just by a carefully measured shift in heat. It's a huge leap in sterilization efficiency. Graphing the z-value, to actually find this vital number, scientists have to transition into the how and why. They plot those known d-values against different temperatures on a semi-logarithmic scale. Our source material highlights a really crucial reality about this entire process. It says, in a perfect world, the d-value of a particular spore will decrease exponentially as temperature is increased. In reality, however, d-values will not decrease perfectly due to natural variations and experimental error. I want to emphasize this because nature is messy, right? It's unpredictable. We can't expect a perfect textbook exponential decrease in a real-world lab, which is exactly why we have to rely on a statistically correct line of best fit to accurately represent what our physical data points are actually doing. Because those d-values are plotted logarithmically, that messy exponential form actually straightens right out and looks like a straight line on our semi-logarithmic paper. Once we've drawn that line of best fit to account for those natural variations we just talked about, the math gives us our definitive answer. The absolute value of the reciprocal of the slope of this line will be our z-value. It sounds like a mouthful, but visually it's brilliant. Breaking this down into 3 simple steps reveals a highly repeatable procedure. Step 1, you plot at least 3 d-value and temperature pairs on your semi-logarithmic graph. Step 2, using your best judgment to account for experimental error, you draw a straight line of best fit that most closely aligns with those points. And finally, step 3, from that line, you simply determine the number of degrees required to change the d-value by one factor of 10. It takes this highly complex mathematical theory and turns it into a clear, visual, and totally repeatable procedure. Let's move to and see how this builds when we apply it to a real-world scenario. Imagine a lab followed those exact 3 steps, plotted their bacterial data, and analyzed their graph. In the specific example provided by our sources, running this graphical calculation shows us that it takes an 8-degree shift to change that d-value by a factor of 10. So our z-value for that specific hypothetical spore population is approximately 8 degrees Celsius. We have covered a vast amount of ground today, traveling all the way from foundational statistical formulas measuring distance from a mean right into the intense literal heat of microbial sterilization. But as we wrap up this explainer, I want to leave you with this final provocative thought. How do these invisible thermal thresholds dictate the absolute safety of the canned food sitting in your pantry right now, or the medicine currently stored in your bathroom cabinet? Every single day, your health and your life is quietly protected by food scientists and pharmacologists who map out this exact mathematical curve to ensure dangerous bacteria are systematically and completely destroyed. It's not just abstract math, guys. It is a literal shield. Thank you so much for joining me, and as always, keep seeking clarity in the data around you.